These next nucleophiles, carbon-based nucleophiles, will allow us to make new carbon-carbon bonds, so they are quite important. We've seen some of them before. Just briefly, let's look at the Grignard reaction. We've drawn this mechanism many times before, so I'm not going to spend a lot of time here, but we know that it's two steps. We've added a carbon-carbon bond. A ketone gets turned into a tertiary alcohol. Aldehyde would get turned into a secondary alcohol. So next, let's look at the cyanohydrin formation. So we'll take a generic ketone. We're going to add a mixture of HCl and potassium cyanide. And this is basically going to react as though it were hydrogen cyanide. So strong acid and potassium cyanide mixed together, they do make hydrogen cyanide. The first step, of course, in any acidic catalyzed mechanism is to protonate the carbonyl. And then we have got a good nucleophile here. Cyanide acts as a good nucleophile, and that is the final step in this mechanism. We've made a cyanohydrin. So that's the cyanohydrin, and it's useful in itself because we've now put a new functional group on. But more importantly, we could do a couple of other reactions here. We could take lithium aluminum hydride. We would need some excess lithium aluminum hydride because probably the first hydride would react with this H, so we need to be careful about this addition. The second hydride, remember there's plenty of hydrides on a lithium aluminum hydride molecule. The second and third hydride would react with the cyano group, reducing that CN triple bond to a CN double bond, and we would get a molecule that looks like this. And there are two H's here that I should draw. We might actually draw it like this in the future just to save space. But those are the same molecule. And so you can see that we've taken this ketone, we've retained that 4-carbon chain, but we've added a carbon and a nitrogen now at the carbonyl carbon. So we've increased the functionality present, we've increased the utility, and we've increased the carbon chain by 1. Another reaction we can do with the cyano group is simply to heat it up in the presence of acid and water. And if we do that, we essentially turn the CN triple bond into a number of CO bonds. So we get 3 CO bonds here. We turn the CN group into a carboxylic acid group. And so again, we've added this piece to our ketone, almost as though we were able to take a carboxylic acid as a nucleophile and add it to a ketone, or take a carbon bearing an amino group as a nucleophile and add it to the ketone. Now obviously we can't do that straight away, but we can do that in 2 steps now through this cyanohydrin formation and then one of these 2 options that I've outlined in blue. Another really cool reaction we can do is called the Vidiq reaction. This is Nobel Prize winning chemistry. Georg Vidiq was a German chemist who won the Nobel Prize in, I believe it was the late 70s. For his research along these lines. Here's the general basis. We take a ketone or aldehyde. We make a phosphonium ylide. So this is 3 phenols attached to a phosphorus, and that phosphorus is attached to a CH2 or a longer carbon chain, but the carbon is an anion. It's got a lone pair. It's missing one of its 4 bonds, and the phosphorus, having 4 bonds instead of the normal 3, has a +1 formal charge. So this is an ylide. It's a new vocabulary term. And that simply means a compound that has opposing charges adjacent to each other. We've got a positive charge on one side, negative charge on the other. Another way to think about this ylide is this way. Because you could draw a resonance structure then that puts the double bond between the P and the C. Now, of course, this gives 5 bonds to phosphorus, so some of us are uncomfortable with overfilling the phosphorus even though it is in period 3 on the periodic table. So most of the time we're going to see our ylids in this form. Okay, so I mix my ketone with the ylid. The product is this. Can you see what happened here? I've traded the O on my ketone for the negative alkyl group on my phosphonium ylid. So I've made a alkene out of my carbonyl. Do you remember how to go in the other direction? How could I make the carbonyl from my alkene? Remember from semester 1, the ozonolysis reaction is basically the reverse of this, where we cleave the alkene and we end up with a carbonyl. So now, anytime you have a ketone or aldehyde, that could be a alkene instead with one reaction, one step. So let's look at the mechanism of this. The negative charge of the phosphonium ylid acts as a nucleophile, as you might expect. And then we call this a beta-ine. I'm not sure that that vocabulary is that important, but that is what we call it. And then we are going to make a 4-membered ring by making a bond between the O- and the phosphorus. Now we have no charges here, and you can sort of see how we've already made the carbon-carbon bond, right? We've made the PO bond that we're going to eventually have. Now it's time to break the CO bond and break the PC bond. And we can do that at the same time through an arrow push with 2 arrows like this. We're sort of breaking apart this cyclic structure, and we're left with the alkene plus triphenylphosphine oxide. And so we're able to, again, turn a ketone into an alkene. So how do we make this Vidiq reagent? Let's look at that. We take triphenylphosphine, which has a lone pair on the phosphorus, much like a nitrogen with 3 bonds would have a lone pair. It is a very good nucleophile, and we can react that with any good SN2 candidate alkyl halide. Pretty much primary are most useful, but we need to be able to do a good SN2 reaction on these alkyl halides. So methyl iodide is great, of course. It's very unhindered, but any primary iodide or bromide would work just fine. And we perform an SN2 reaction. We make triphenylphosphine or methyl triphenylphosphonium. Let me draw that again. It's not how I wanted it. Okay. So now we've got a cation on the phosphorus. What we need to do, if you compare this molecule in purple to this one up here in blue, you'll notice that all we need to do is remove an H off of the methyl group, and we have our phosphonium ylid. So we react that with a very strong base, typically N-butyl lithium. This is butane with a lithium on the end and a very strong, very basic anion on this carbon. So this will remove that H and provide us with the ylid. And so that's how you can make a phosphorus, a Vidiq reagent. Again, I would recommend choosing primary alkyl halides here. Triphenylphosphine is easily purchased. It's very cheap. We get that from the chemical company. Mix our reagents together, do an SN2 reaction, and then deprotonate the formed phosphonium ylid using N-butyl lithium to make, sorry, that's not a phosphonium. Deprotonate the phosphonium cation using N-butyl lithium to make the phosphonium ylid. Let's look at a few examples of how we might use the Vidiq reaction in synthesis. Perhaps the question says, produce this compound using a Vidiq reaction. And we can observe there's an alkene here, so we could actually do it 2 different ways. We just need to cleave the alkene and decide which half gets the phosphonium ylid and which half gets the ketone. So let's Let's cleave it and put the ketone on the upper half. And the phosphonium ylide then needs how many carbons? We need to add 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5. And I'll put the anion here, plus on the phosphorus. So mixing these two reagents together will get us to the product. And how do I make this phosphonium ylide? Well, I could take triphenylphosphine plus the 5-carbon alkyl halide, and I could use the bromine. I could mix them together as step 1. Step 2, N-butyl lithium will deprotonate, giving me the phosphonium ylide. And as we saw on the previous slide, this is a primary alkyl halide. That's a perfectly reasonable substrate to use in this SN2 reaction. The other option would be, let's use a different color. The other option would be to make the upper carbon piece our ylide, and the lower carbon piece, the 5-carbon chain, the carbonyl. And so how would we make this ylide? Well, we could use this alkyl halide, triphenylphosphine, mix them together. Second step, again, butyl lithium, and that's what we're going to make right there. Which of these proposals do you like better, the green one or the red one? Really, the difference is that this nucleophile is a little more hindered because it's a tertiary carbon anion, whereas over here we've got a secondary carbon anion. So the green nucleophile might be a little better. Making the green phosphonium ylide from the primary alkyl bromide is probably a little easier in an SN2 fashion than it is from this secondary alkyl bromide. So I'd say the green choices are probably better in this case. It's easier to make the ylide, and it's easier to do the nucleophilic attack on the carbonyl species. Even though over here the aldehyde is more reactive, I think that just these 2 points here, primary and less hindered carbon anion, are going to be a little easier for us. Let's look at one more example. So here we have an alkene, and again we can cleave that and probably make the Vidiq product 2 different ways. And I think that if you're following along, you'll realize that, as we learned up on the top reaction, if we make this carbon our nucleophile and this carbon the carbonyl carbon, the electrophile, that makes for an easier time. It's a better nucleophilic attack by the carbon anion, and it's a better SN2 reaction to prepare the Vidiq reagent. So I think we want to do that again. I think this should be our carbonyl carbon, and this should be our nucleophilic carbon on the Vidiq reagent. So we're going to cut this in half. I'm going to make my carbonyl species, and I'm going to make my Vidiq species. And I have that ylide. And again, I can make this ylide via that alkyl bromide, mix it with triphenylphosphine, and second, I can deprotonate with N-butyl lithium. So this is a primary alkyl bromide. That should be a pretty easy SN2 reaction to make my Vidiq reagent, giving me this compound, which can then react with acetone to make the desired tri-substituted alkene. So those are just the thought processes you want to think about when you're preparing Vidiq reagents.